Hey everyone, we're going to make some zinc oxide nanowires today via hydrothermal synthesis. And the first thing we have to do is we have to get this silicon substrate here nice and squeaky clean. So we're just going to clean it with some ethanol. And you can really hear the cleanliness here. Get that nice little squeaky sound. I'm just going to go ahead again with this microfiber cloth. There we go. Nice and shiny. And now we're going to go ahead and spin coat it with some seed layer solution. So we're just going to dip our pipe in. There we go. Very carefully place it on the substrate. And let her spin. Alright, so now it's done spinning, and we're going to go ahead and take it off and put it into the oven to crystallize. Alright, it's all finished. We're going to go ahead and take it out of the oven and head on to the other room for growth. Alright, so now that we've taken it out of the oven, we're just going to load it into our fancy-dancy sample holder. Expertly engineered with 3D printing. And once our sample is mounted, we now just invert it into solution and let it grow. And we heat it up, we let it stir, and nanowires are growing right before our eyes.
Hi, my name's Brielle Weiner, and I'm part of Act 2, which focuses on the prevention of infection transmission. So mainly what our research is that we'll be building thin layer by layer films out of polyelectrolytes, and then we'll be loading those films with antibiotics to test them against bacteria, to see their effectiveness and really optimize their conditions. And so the main way that we can build the films is with this deposition robot that you can see behind me. And so right now you can see it working. It has very fine sensors in the pipette tips so that it will be able to see the exact level of the liquid in your 96 well plates. And it can very accurately pipette in and out the liquid that you need. So mainly the way that it's used is that it will first pipette in the polycation, wait a certain amount of time, which you program into the computer over here, and then it will do a few rinsing steps, and then repeat the process with the polyanion and work back and forth in order to build up the layers. So as you can see right here in the robot, it's currently removing the liquid from the 96 well plates and disposing of it in the waste bin. And all that has been programmed into the computer over here. So in just a few short hours, the full film will be built, and it will be able to then be used in further testing.
Hi, I'm Alyssa. I'm part of Act 3, and I'm going to tell you a little bit about what I've been working on. So right now I'm using a polarized optical microscope, as you can see here, and we're looking at a sample of 5Cb in an in-plane cell. So we're able to add an electric field. The cell is wired up here, and we can apply different electric field strengths and sort of measure the response of the liquid crystal and see if the application of an electric field is affecting how the particles orient themselves or just how they can be controlled. So right now I have the cell at 33 degrees Celsius, and I'm going to keep the temperature constant while I go through a range of electric field strengths and use this machine to change the electric field strength, and then this machine to conduct dielectric spectroscopy measurements over here on this computer. And so now I'm going to take a measurement, and ultimately the goal is to embed nanoparticles in this material and see if we can use the electric field strengths to control the orientation of those nanoparticles. But right now I'm just taking some baseline measurements so that we can see just if there's a change at all when we add the nanoparticles and apply the same electric field strengths. So I'm at 33 degrees Celsius right now. I'm going to apply an electric field strength of 0.25 volts. We will start taking the measurement, and it takes about 6 minutes to sweep through the measurement. But as you can see, measurements are taken, and this is ultimately just like a measure of the electrical properties of the cell, and we can use this to get the electrical resistance or conductivity.